7 minutes after Apollo 17's cabin began repressurizing, astronaut Harrison Schmitt pulled off his helmet and said something strange to his commander. "Smells like gunpowder, just like the boys said." Gene Cernan answered, "Oh, it does, doesn't it?" Neither man was joking. Every single astronaut who has ever walked on the moon reported the exact same thing, independently, across 6 separate missions. And by every law of chemistry, none of them should have smelled anything at all. Smell isn't a property of a surface. It's a property of the air. Molecules have to physically drift off something, travel to a nose, and trigger receptors there. That process requires an atmosphere to carry them. The moon has, for all practical purposes, none. It's a near total vacuum, sitting in permanent airless silence. On the lunar surface itself, inside a sealed helmet, there was never anything to smell. So where did that gunpowder scent actually come from? It came from inside the cabin, after the helmets came off. Astronauts tracked lunar dust back into the lander on their boots, gloves, and suits. Dust that had spent roughly 4 billion years sitting undisturbed in a vacuum, untouched by oxygen, untouched by moisture, essentially frozen in a kind of chemical stasis. The moment the cabin repressurized and that dust met breathable air for the first time in its entire existence, something reacted. The leading explanation comes from geologist Larry Taylor, who worked as an advisor during the Apollo missions. His theory centers on what chemists call dangling bonds. Lunar dust forms through constant micrometeorite bombardment and solar radiation, violence that fractures mineral grains and leaves their broken surfaces studded with unsatisfied chemical bonds, essentially molecular hooks with nothing attached to them. Taylor proposed that when this highly reactive dust suddenly encountered cabin oxygen and the moisture on an astronaut's nasal membranes, those dangling bonds snapped shut almost instantly in a small burst of chemical energy interpreted by the nose as a sharp, metallic, gunpowder-like smell. That's the leading hypothesis, but it isn't the only one, and it isn't fully settled. Other researchers have pointed to solar wind ions, charged particles from the sun that get physically implanted into lunar dust over billions of years, potentially releasing energy on contact with air in a similar way. Others suspect oxidation involving nanophase iron embedded in the glassy coating that forms on regolith grains. More than 50 years after Apollo, scientists still can't say with total confidence which explanation or combination of explanations is correct. There's one more detail that makes this stranger. When lunar samples are eventually opened and studied in laboratories back on Earth, they don't smell like anything at all anymore. Whatever reactive chemistry produced that gunpowder scent apparently exhausts itself almost immediately on first contact with air, which is exactly why the phenomenon has been so difficult to study directly. The smell announces itself once, and then it's gone. So the next time you picture the moon, don't imagine a place of total sensory silence. Imagine Schmitt, 7 minutes after repressurization, recognizing something in the air that generations of geologists still can't fully explain. Nobody ever smelled the moon itself. They smelled 4 billion years of frozen chemical potential meeting air for the very first time. And that brief, sharp reaction remains one of the moon's last genuinely unsolved mysteries.